Hi everyone. Today I'm going to talk about our recent project on simulating polymers using a mesoscale model called Discos. So I'd like to first acknowledge all the collaborators in the group and any other researchers from other institutes for their help and support on this project. So let me start with some background. Polymers are widely present in nature as well as in the industrial applications. Some natural polymers include rubber, wool, and many biomolecules such as DNAs. People also have synthesized many polymers such as plastic, Teflon, and epoxy. If we look at these applications, the relevant length scale is on the order is at macro scale, which ranges from several centimeters to meters. The versatile functionality of polymers comes from its complex constituents and structures. So at micro scale, polymers consist of basic units called monomers, represented by these circles and squares here. So in a way, polymers are really like bead necklaces. One can already have random alternating and block structures for just one chain. And with the multi-chain structures such as branching, cross-linking, and network, one can have almost an infinite number of configurations. And each of these configurations can have a unique function. But the typical size of the monomer is only on the order of 1 angstrom to several nanometers. So it's like a 7 to 10 orders of magnitude difference between macro and micro scale. That's the difference between the whole Bay Area and one ping pong ball. So it's not possible to resolve every detail up to the application scale. That's why we are interested in the mesoscale model. Meso means intermediate, meaning that we only resolve part of the details, and coarse grain the rest, while capturing the physics at larger scales. So the goal of this project is to develop efficient methods to simulate polymers at mesoscale that can be scaled up to facilitate material discovery and process design. So since polymers are important in many areas, there already have been many studies out there, and the simulation is a big part of it because it's a powerful tool to access many length scales. But because the separation of length scale is so large, a full physical model is still lacking. So on one hand, molecular dynamics is a good method to get down to every atom. But explicitly modeling every atom is computationally expensive. So here is an image of all atom simulation of starch polymers in water. We can see that there are only about 10 chains of polymers in there, and the rest of the space is filled with those small water molecules. There are other studies focusing on implicit solvent model, meaning that the solvent is giving polymers a resistant force, but it's not explicitly resolved. This method is also problematic because it does not capture the full hydrodynamics, which is especially important in biological cells. On the other hand, a continuum model can go to macro scale. Here is a simulation of a mixture of two model polymer blends. And the box dimension here is on the order of microns, but can easily extend to larger length scales. But for this kind of simulations, all the microstructural details are ignored. And as a result, some of the molecular scale physics cannot be captured. So we have developed a new mesoscale method in the lab called Discos. Discos stands for discrete ion stochastic continuum overdamped solvent. The name already tells us the essential element of this method. So the solutes are modeled as discrete particles, and the solvent is modeled as continuum with thermal fluctuations. One advantage of this method is that it can capture the full hydrodynamics without inverting a dense mobility matrix. So it's like a cartoon here. So the problem of polymer is both multi-scale and multi-physics. So we choose to develop this model in the AMX framework. So AMX combine all these multi-physics with advanced high performance computing features such as load balancing and mesh refinement with multiple layers and efficient solvers and the GPU capabilities. So on the Lagrangian side, we solve fluctuating hydrodynamics and the electrostatics. On the, sorry, this is Eulerian side. But on the Lagrangian side, each particle experiences a total force that can come from electrostatics, short-range interaction, and external forcing. And each particle move follows the overdamped Brownian dynamics. So the grid data and particle data are coupled through the immersed boundary method. By choosing the immersed boundary kernels, we can determine the effective hydrodynamic radii of the particles, which allows us to employ another degree of coarse graining via wet and dry diffusion to save computational cost. The wet diffusion part is directly solved from the FHD equations, giving this V here. And because we solve that FHD equation on coarse grid, because the coarse grid gives a large hydrodynamic radius that under-resolve the particle's total diffusion. So we add back the Brownian motion to recover that. That's the dry diffusion part. So here are the overall steps within one time step. First, we spread the charges row onto the grid using the IB kernels, and we then solve the electrostatic Poisson's equation for the electropotential phi. Second, the electropotential is interpolated back onto the particles to calculate the electrostatic force. And meanwhile, particles also collect any other force acting on them to get a total force. Third, the total force for each particle is then spread onto the grid to solve the FHD equation for the wet velocity V. And finally, with wet velocity and the dry diffusion corrections, we update particle position X. So to test this model, we set up a simplified case where polymers are modeled as springs and beads. We simulate a single chain 32-bead polymer in water. For now, we just ignore electrostatics. So the particle only interact via 12.6 Lennard-Jones potential and the Finney springs. We also set the box length to be around 60 times the average spring length, so that we reduce the polymer interaction through the periodic images. So here I will show a movie of our model polymer moving in water under Brownian motion. Each particle is colored by its ID number, and the white lines here represents the springs. So you can see under Brownian motion that the polymer deformed into multiple configurations, and if you take a look at any snapshot like the one here, you can see some zigzag structure, some linear structure, and sometimes there's a ring type structure. And each of these structure can correspond to a certain function. To look at it more quantitatively, we measure both the static and dynamic structure factor of the model polymer. On the left, I first show the static structure factor as a function of wave number. So the wave number is the inverse measure of the length scale. The larger the wave number, the smaller the length scale. And the static structure measures the abundance of structure corresponding to a certain wave number. So we can see this k to the negative 1.7 scaling in the intermediate range, in the intermediate wave number range. This is this matches Flory's theory. And on the right, I will show the scaled dynamic structure factor versus time for different wave numbers, and also show the unscaled data in the inset. The dynamic structure factor is a measure of persistency of the structure corresponding to a specific length. And because as time goes on, the structure relaxes and the dynamic structure decreases, as we see in the inset. Interestingly, with the scale data with z equal to 4 collapse all curves onto 1, which matches exactly the Doi and Edwards prediction for the Rouse model. So to conclude today, I present our preliminary work on modeling polymers at mesoscale using a discourse method. We anticipate a lot of exciting work coming out of this project. We already start simulating active swimmers such as Flagella with the collaboration from the University of Central Oklahoma. Here I show a snapshot of one flagellum swimming in fluid and shows the velocity and the pressure field around it. And we're also interested in the transport property of polymer tethered membranes. So the figure here, the cartoon here shows kind of how the solids can be trapped by the polymer network, and which in turn affects the flow property. So I will stop there, and I'd like to take any questions. Thank you.
So thank Galen for this interesting talk. Now, are there any questions from our audience?
Good talk. I have one question about the setup for your model. So is the coupling between the microscopic scale and this macroscopic scale, is it two-sided, connected somehow? Or is just one-sided? Like, for instance, in your fluctuation hydrodynamics equation, it has influence to the Brownian motion, right? Does the Brownian motion have the effect to
yes, it is two-way coupling, because the particle experience a force on them. It maps back to the grid to solve for the fluctuating hydrodynamics equation. Then because we solve for the fluid velocity, that affects how particle move for the next time step. So it's like a two-way.
Two-way side.
Yes.
Okay, thank you.
Thanks for the question. So are there any more questions? Maybe from our online audience? So if there are no further questions, we will thank Galen again for this interesting talk.